Welcome to this video number 11, exercise 618, RCL, parallel resonance circuit and solution. We see here the parallel resonance circuit with a resistor, capacitor, an inductor, and a current source. In this exercise 618, we have this information that the resistor is 10 kilo ohm, the inductor is 100 microhenry, and the capacitor is 500 picofarad. Find the resonance frequency, the quality factor, and the bandwidth. After this slide, the solution will be shown. Stop or pause the video. Try to solve the exercise yourself first before you see the solution. First, we have to find the resonance frequency. We apply the equation for the resonance frequency. We have it here. The resonance frequency is 1 over 2p square root and then L times C. We have both values, the inductor and the capacitor. So placed here, calculating, we get 711.8 kilohertz. Then we have to find the quality factor for this parallel resonance circuit. We can either use the parallel resonance where we have the resistor and the inductor, or the resistor and the capacitor. In this case, we just use the resistor and the inductor. Omega 0 here is 2 times F0, the resonance frequency. So placing the information about 10 kilo ohm and the inductor 100 microhenry, and our resonance frequency here times 2p, we get 22.36 as a quality factor. The bandwidth can be calculated based on the resonance frequency divided by the quality factor. So we take this result and divide by our quality factor result, and that gives a bandwidth of 31.83 kilohertz. The next step in our solution is to verify our solution. We do that by a simulation. I have here simulated the circuit in anti-spice, and I use a current source and a component, and we can see here the Bode plot of the circuit. The highlighted line is the magnitude in dB, and the dotted line is the phase shift. And we know the resonance frequency can be found at 0 degrees. That's easier than trying to find the top of the filter. We go in with the cursor and identify that it has 712.8 kilohertz. That's very close to the calculated value. And at that point, we have a magnitude of 65 dB. So it's actually amplifying the signal. And we have a phase shift very close to 0 here. If I have zoomed in, I could have hit the spot better in 0 degrees. Then we have to verify the half power frequencies. We go in and look where we have a drop from the maximum down to 3 dB. So we go in at these 65 dB we had, and then 3 dB down, that would be 62. And we have two different frequencies, 892 and 312 relatively. That's end of video 11. Thank you for watching.